Okay, I'm going to work this out just for a general matrix. Okay. Instead of backwards apostrophe, I'm just going to use A. So A equals 1, A, 1. So that eigenvectors for the eigenvalues. And the eigenvalues and this, of course, gives you one minus lambda squared minus A squared equals 0. Okay. Which is then 1 minus 2 lambda. I wasn't trying to write this weird thing. It looks like a 7. The chalk just kind of stuck on me. Okay, come on. It needs to cooperate here. I make plenty of mistakes, so I'm not trying to cover a mistake. It just really doesn't stick on me. Okay, 1 minus 2 lambda plus lambda squared minus A squared equals 0. So that you have lambda squared minus 2 lambda minus I'm going to write it this way, the quantity A squared minus 1, because I want to write this as one quantity. And this equals 0, okay? Well, A squared minus 1 is A minus 1 times A plus 1. Okay. And well, it's usually you to verify that see if I've got this right. Okay. So multiply A minus 1 and A minus 1, I get A minus 1 times A plus 1. And since this is negative and this is positive, I get this, right? And then, just factoring, if I add this to this, I get plus 2 lambda, don't I? Because A minus 1 times lambda plus A plus 1 times lambda gives me plus 2 lambda. I get a minus 1 lambda out of this and a plus 1 lambda out of this, and I don't care lambda. Wait a minute. So it looks like I need those things I don't ponder on video time. Okay. Yeah, I looked at switching the signs here, and it bothered me because, well, we got rid of the A's. Well, we got rid of the A's because we don't have an A in lambda. I've got an A lambda and a minus A lambda gives me then my minus 2 lambda, doesn't it? Okay. Minus 1 lambda here, minus 1 lambda here. And I worked out a numerical example. I just picked a number A. But whatever number you pick for A, whatever number you used for A, depending on the number of letters in your first name, it's all going to work out. That's the point here. So that lambda equals a plus 1 or a minus 1. Okay. Now, notice this strategy. I mean, I had to use it before I saw the bonehead thing I did here. If I'd have written all this out, it would have worked. Okay. But I was shortcutting it. If you expand this, you get this. And if you understand factoring, you can kind of see how that factors. Okay. Whether you would actually see this from this or this, well, that's an algebra trick. Yeah. As you do more and more algebra, you learn to use tricks like this. And then hopefully you won't screw them up like I just did. Okay, so there it is. Now I think I can finish this here. And we got, I can't quite see the whole thing. And there. Okay. Now we got to figure out the eigenvectors, right? So here we'll call this lambda 1 and lambda 2. Okay. So well, actually, we've already got that in there, so now you can see that. So we have the matrix, augmented matrix, 1 minus the quantity A plus 1 is negative A. That's A, right? And then this is A and this is negative A. So we very quickly, well, we reduce this matrix if you wish. But the equation you get here is just a multiple of the equation you get here. So we know that. So I'm just going to say that, well, x1 equals x2. That's your eigenvector for lambda 1. And then lambda 2 is A minus 1. And we get this. But this is just A, and this is just A. So This is an eigenvector. Okay, and everybody got that. I mean, you could have had -1 here and 1 here. It's arbitrary. You just got to choose a multiple of this. Okay, and then relative to basis. I won't abbreviate it too much, but we've been using A prime for the new matrix, and that equals inverse A P. P, the column, the matrix consisting of column vectors of this basis. Okay. Now, P inverse, which you can actually get by inspection here, turns out to be, let's see, 1/2, 1/2, 1/2, 1/2. Some of the 1/2s are positive and some are negative. Now, this row times this column has to equal 1. Okay. So that one of these 1/2s is going to have to be negative. This one negative. Because if I now multiply this by this, I get 1. So my first row, this row times this column gives me 0, and this row times this column better give me 1. Okay, and this row times this column better give me 0. So that's all I'm put the negative there. I'll put it here. Because now this row times this column is 0. This row times this column is 1. Well, I don't have enough room, do I? Yeah. Just put it all in one line. I'll just write my P inverse P a little small. Actually, give myself plenty of room to write it up here. Well, 1/2, 1/2 here gives me 1/2 of A plus 1, right? And here it gives me same thing. Down here it gives me 1 minus A over 2, because half of 1, negative 1/2 of A. Okay. Now here it gives me A minus 1 over 2, which is just the negative of this. I could have written one of these as the negative of the other. It might have been clearer, but I didn't want to confuse the issue. I'm making it clearer. Okay. Just a choice. I'm not sure I made the right choice, but there's a step if I put the negative on there. That might be a little confusing. Anyhow, we do this and we get what? A plus 1, and we should get I'm getting 1 minus x, so that's all right. Okay. Then, yeah, I mean, they're like 2 columns in this thing. So I'm not sure what I was thinking when I wrote that down. But okay, this gives us a plus 1. And this gives us 0. And this gives us 0, obviously, since this and this are negatives. And then this gives us this minus this, which is a minus 1. Okay. So what you should have gotten down here would be a diagonal matrix with a plus 1 and a minus 1. So if A is, okay, what were your values of A? Well, what have you had? 3, I think, for the value of A, right? Okay. If A is 3, you're going to get 4, 2. Okay. And if A is, what other values? 4, if A is 4, you're going to get 5, 3. Okay. Which is, of course, what you're, where is it? What you factored. In other words, your eigenvalues. Okay. And what were your values? What was your value by? 4? Okay, well, you would have gotten that 5, 3. Okay, if you did everything right, if you did all your arithmetic right. So if you didn't get it right, check your arithmetic and see what went wrong. I know I looked closely at least one of them and I couldn't spot it. But I tend to believe what I see, so I got to look really carefully. Got to know what I'm supposed to get. Okay, so what this is then is lambda 1, 0, 0, lambda 2. This is a particularly simple matrix. Obviously, it's easy to multiply by other matrices. Okay, if you multiply this by a vector, you're going to get lambda 1 times that vector. Okay. Or lambda, well, what I should is write it out. Okay. So there we have the fact that at least for this symmetric matrix, where we have 1s in the diagonal and just any number on the opposite diagonal, as long as it's the same one. So if the matrix is symmetric, we get the eigenvalues on the diagonal. Now, if I'd have had 2 different numbers, instead of 1 and 1 on the main diagonal, it would have still worked out, but the algebra would have been a little, I could have put BC on the diagonal. Okay, it didn't have to be 2 1s. But to keep the algebra simple, I use 2 1s, and you can convince yourself. You could do the matrix. I mean, even like the matrix A, C, C, B, okay? Or A, B, B, C, okay? Whatever. As long as it's symmetric for a 2-dimensional 2x2 matrix, and it wouldn't be a bad exercise to prove that to yourself. But this illustrates things. Okay, like for one thing about this matrix, if I wanted to calculate the 10th power of my original matrix, what's this matrix to the 10th power? Well, if you multiply this matrix by itself, what do you get? You get 1 plus a squared and a squared plus 1, okay? And then the next power gets a little more complicated and you get more and more terms, okay? It's a mess. And if it isn't, well, put different numbers in the diagonal and it'll be a real mess. But what's the 10th power of this matrix? It's lambda 1 to the 10th, lambda 2 to the 10th. Okay. So 8 to the 10th is a mess. Okay. Now, to see why that is, go ahead and start multiplying. Multiply this matrix by itself. Well, the row times the column is going to square lambda 1. The row times the column down here is going to square lambda 2. Okay. And the other rows times columns are going to give you zeros, because this row times this column is going to match zeros up in both. So I don't want to write that out, but I recommend you write that out to convince yourself that it really works. Okay, this is really kind of important because this allows you to do a Taylor expansion of a matrix. Okay, and you gotten into Taylor series by now, haven't you, in calculus? No? Yeah, it's coming up soon. Don't anything in sequence in the series? Okay, so Taylor's coming up real quick. Okay, it's really neat. It's not hard, as long as you just do a few of them, and as long as the derivatives are easy enough. Okay, I mean, it's real hard if you got something that you can't take infinite number of derivatives of. Okay, but like for sines and cosines and exponentials, it's very simple. And polynomials, especially because a polynomial is its own Taylor expansion, stuff like that. Okay, so you can do a series expansion of a matrix. You can do powers of the matrix this way. Now, what does that do for A? Well, now A prime is P inverse AP, so A is P, A prime, P inverse. Make sure you understand the manipulations of that. It's very straightforward. You just multiply on both sides by, multiply on the right by P inverse, multiply on the left by P, and that becomes that. Okay, we've done that. Not going to take a lot of time to do it. Okay, so A to the 10th is this. And I'm going to say, well, that equals P A prime to the 10th P inverse. Why is that? It's because it's important to understand this. I got 10 of these strung out by the associative law. These match up, and these match up. You just have a bunch of identities in between, and the only ones that don't give you identities are the ones at the beginning and end. Is that clear? You've seen that, haven't you? You've read that? Okay, reading. Okay. So there are a few steps. But they're straightforward. It's kind of important to understand that. And this is a lot easier than trying to do 10 multiplications of A by itself. Now you could shortcut that. You multiply A by itself to get A squared, right? And you multiply A squared by itself, you get A to the 4th. And multiply A 4th by itself, you get A to the 8th. You multiply that by A squared, and you've got A to the 10th. So you've only got to do like 4 or 5 multiplications, but it's still a mess. And that whole deconstruction of the binary sequence of matrices, I'd like to have time to talk about that because it's kind of important, but we're not going to, most likely not going. Okay, so anyhow, that's one example of why it's so wonderful to be able to diagonalize a matrix. because a lot of times you do want higher powers or to do other kinds of algebra with matrices. You reduce the power diagonal matrices, do the algebra with the diagonals, then transform back. It's like a commutative factor. You got your A prime here and your B and W. And then up here, you've got your A matrix with V and W, and your P inverse going this way, your P going this way. A commutative diagram that you always want to understand. Yeah, you always want to have that in front of you. Okay, at least from now till the end of this course, and very likely in later courses where we have to use it. Okay. Now that's kind of a digression. But this illustrates a number of properties of symmetric matrices. Now, first of all, your definition of a symmetric matrix. The matrix that equals its transpose. Now in the matrix you use, you just have one number to transpose, or one, they're just a secondary diagonal transposes, okay? And your rows become columns, and you can see very clearly that your matrix is equal to its transpose. And that's what makes it symmetric. Your rows become your columns, okay? Okay. Now, got a symmetric matrix. An n by n symmetric matrix. Okay, so I'm saying an n by n symmetric matrix A is symmetric. I didn't put a lot of words in there, probably should have, but I did. Okay, the n by n matrix A is symmetric if and only if. And n's real eigenvectors. Okay. So it has n real eigenvectors, it's symmetric. If it's symmetric, it'll have n real eigenvectors. Now that's a big one. There's an obvious, if you look at the matrix, these things are obvious. So what else? I'm having a senior moment here. I'm actually going to take a look. The obvious thing. We've been using all along, it diagonalize them. Okay. And another thing that isn't relevant to the matrix we have, but you can have repeated eigenvectors, right? And you've done examples in your homework where you have repeated eigenvectors. I'm paraphrasing the way it's stated in the book. Maybe this is more intuitive, maybe it's a bad statement. if an eigenvector repeats and I'll use k times, as you go back, let's use k. An eigenvector repeats k times. You'll get k. That's an eigenvalue repeats k times. Eigenvectors don't repeat, eigenvalues repeat. An eigenvalue repeats a times, k times. You get k. You get k independent eigenvectors. Okay. And that's one that we're probably not going to deal with in an example today because you'll see it in your text. But the point now is these three conditions imply that you have n independent eigenvectors. Okay. We get n real linearly independent eigenvectors. I'll give these names V1 through Vm. So you can diagonalize with P equals V1, V2, Vm, which, if you need reminding, you probably don't, but means the matrix with these vectors in the columns, okay? Now, that's exactly what we just did, okay? We put our eigenvectors in the columns. We calculated the inverse, which you can always do. Might be a mess, but you can always do it, okay? And if it's a big matrix, you do it by row reduction, you don't do it, well, by any other method. Inspection is going to work, for example. And inspection might not work for you, depending how well you see this. Okay. Well, that's pretty much it, except that it's a real advantage if we have an orthonormal set of eigenvectors. So we're going to actually work that out for this matrix and see how it works. If we had time, I'd have you work it out, but we've got like 14 minutes left, so we better get to it. Okay, so in our example, the basis of B prime is 1, 1, 1, negative 1. Now, these are orthogonal, but they don't have to be orthogonal. And if they aren't orthogonal, how are you going to get an orthogonal basis? Well, you're going to use Gram-Schmidt. So you better be up in Gram-Schmidt, okay? You're going to get reminded. You're going to have to use it. So So we're going to be able to assume that B prime is an orthogonal basis. So in our example, we don't get, because our example is particularly simple. And at this point, you ought to ask yourself a question. What if I didn't have those ones in the diagonal, but it's two different numbers in the diagonal? Would I still get an orthogonal basis? Okay. Anyhow, that's something that if you have time, you want to be able to think about things like that and work them out. And it's worth trying to make time to do that, but not at the expense of things like showing up for work on time, getting your homework done, and I recommend you try to think about things like that once in a while. Ask yourself questions, be curious about it, because that's how you can develop a deeper understanding. Okay. Okay, anyhow, if you get a non-orthogonal basis, use Gram-Schmidt. So let's go ahead, this is orthogonal. Now we want to get an orthonormal basis. Well, I'll call it B double prime. And this should be a operation on the graphic. This is orthonormal. How do you get an orthonormal basis? If you got an orthogonal basis, you just divide every vector by its magnitude. Magnitude of this vector is square root of 2. And dot product of the vector with itself is square root, right? Dot product of this with itself is 2. Square root of is 2. Or just think of it as a theorem. Okay, so this is orthonormal. Now, using this basis, what would our matrix A prime be? Yeah, okay. Now that works. This times this gives me 1. This times this, well, signs are opposite over here, gives me 0. Signs are opposite here, they are here, so I get 0. And the signs match up here and I get 1. Okay. Note that P inverse equals P transpose. I'm going to kind of throw it out as an open question. You're going to have to read to find out. That's a prominent idea, if it's true. This makes it easy to do the inverse matrix, doesn't it? If you have an orthonormal basis. Okay, well, it's true. But read it anyway, okay? So A double prime, which is your matrix relative to this basis, is P inverse A2 transpose. So if this is always true, that saves you a lot of trouble. Well, since I already gave it away and says it's always true, said it's always true, let's explain why it's always true. Okay. And just for a, well, okay. You see what I'm writing? This is just A11, A21 up down through AN1, okay? In other words, this would go in the first column of an AMN matrix, right? Or ANN matrix in this case. And this would be I wrote it down wrong. So it's a good thing you can't see what I wrote. If you can't, I apologize. Okay. You know, don't just pick any old pattern and write it down. You think about the pattern. If you can think while you're talking, apparently I can't. Okay, so that'd be A22, and this would be AN2, and so forth. These are orthonormal, and your matrix V1, V2 up through Vn has these orthonormal vectors in the column. I multiply this matrix by its transpose. What do I get? Well, the rows become the columns. The columns become the rows. So what do I have? My first column here is V1. My first row here will be V1. So that my first let me write it this way so I can just gonna make more sense. And of course, it's gonna be true the other way because of what we're gonna get. But okay, now my first row is the V1 vector and my first column is the V1 vector. So if I multiply the first row by the first column, I get V1 dot V1. Okay. Like if my vector is 1, 2, 3, which it wouldn't be if it's orthonormal because it'd have to have magnitude 1. But if the first column is 1, 2, 3, then the first row over here will be 1, 2, 3. And if you dot 1, 2, 3 vector with the 1, 2, 3 vector, you get 1 squared plus 2 squared plus 3 squared, which is the square of the magnitude of V1 dot V, the magnitude of V1, okay? So this is the square of the magnitude of V1. And this will be the square of the magnitude of V2. And we have just a bunch of zeros everywhere else. There's our diagonal. But since this is orthonormal, every magnitude is 1. So the squared magnitude is always going to be 1. So you get the identity, and therefore the transpose is inverse to the matrix, okay? And of course, the matrix is therefore inverse equal to the transpose. So if I reverse these, it wouldn't make any difference, okay? I could transpose both of these and get the original matrix times the transpose of this, because the transpose of the transpose is the original, okay? So if the P matrix is your column of eigenvectors, this is your P matrix, this is your P inverse matrix. Okay. Now, that's worth understanding. Now, when you put all that together, you get a really neat, succinct picture of transformations governed by symmetric matrices. Now, we're not going to be able to do the whole subject of quantum mechanics for the end of the semester. I know you'd love to. But we're going to move into complex matrices after system. We'll talk about that. We might talk about it Wednesday, but we might go back and do linear regression. Okay. Doesn't have to be linear. Polynomial regression. Okay. And I'll debate about that. Y'all did well on the quiz today. You were able to construct most of this up to the orthonormalization. And of course, you did it with numbers, and there it is with symbols. Hopefully that gives you what you need to understand these properties and read the text and understand the problems as deeply as you can, because it's just important stuff. Very powerful stuff. Okay, it's also really, really neat. So hopefully you have time in your life to stop and smell the roses and see how neat this is. And if you don't find it neat, that's okay. You can still be a good engineer with no aesthetic qualities whatsoever. No aesthetic appreciation for mathematics. I'm sure you got aesthetic appreciation for other things. Okay. It's a tool, powerful tool for engineers, but it's also very, very neat. Okay, one student got everything very quickly. It looked really good. I looked at his paper and said, yeah, that looks good, without really thinking about what we should see, because I didn't really look at his value of A and didn't look at the details that closely. But there was a problem with his arithmetic, and he didn't get quite the matrix he should have gotten. And that and it came up after class A, we did the matrix, the arithmetic came up well. Well, the whole thing I did with the A is a good way of debugging the whole process, at least for a 2x2 matrix. And if you run into a problem and can't find the arithmetic error, if it's feasible, use symbols and see if what you get with the symbols then matches what you get with the numbers. In other words, if you substitute your value of A at the end here, all the steps ought to match what happens with the A. So it's kind of a debugging tool. And we make these mistakes. You see me make them all the time. Okay, but the difference is that I'm always alert to check it. Okay, it doesn't mean I always do it. Sometimes I go on and I don't. But if you're experienced, you become alert to the need to always check what you're doing and always verify it. To the extent of even, you have these theorems, well, you ideally have the reason for these theorems in your head, not a memorized formula even, something that you understand deeply. Now that's a stretch for a linear algebra course taught at this stage in your mathematical education. But you kind of want to be alert to that whole process, to understand things as intuitively as possible, and at the same time as rigorously as possible. So just a plug for rigor, understanding proofs, understanding and using proofs to understand relationships more deeply.